The greatest crime in the history of the universe happened 13.8 billion years ago and lasted less than 1 second. The victim was antimatter, every last particle of it, annihilated so completely that not a single atom survived. The perpetrator was an unknown physical process that broke the laws of symmetry, tipped the cosmic balance by 1 part in a billion, and has never been caught. We know the crime happened. We know the approximate time. We have the evidence, you, me, everything, spread across 13 billion light-years of space. And we have absolutely no confirmed suspect. This is the story of the greatest unsolved case in physics. And the detective work is still ongoing. Imagine you light a match. For one brief moment, there's a tiny explosion. Heat, light, energy. And then, nothing. The match is gone. The air around it is gone. The table it was sitting on is gone. The room is gone. The building. The city. The planet. Everything the explosion touched, erased. Not burned. Not scattered. Erased. As if it was never there. That is what should have happened to the universe. 13.8 billion years ago, the Big Bang didn't just create matter, the stuff that makes up stars, planets, you, your coffee, your regrets. It created matter and its perfect opposite. Antimatter. In exactly equal amounts. Positive and negative. 2 sides of the same cosmic coin, flipped at the beginning of everything. And when matter meets antimatter, they don't coexist. They don't negotiate. They annihilate. Completely. Instantly. Both disappear in a burst of pure energy, gamma rays, photons, light that carries no mass and builds nothing. So the math is clean. The physics is elegant. Matter plus antimatter equals 0. The universe creates itself, destroys itself, and leaves behind a perfectly empty void filled with nothing but radiation. No stars. No galaxies. No periodic table. No biology. No history. No you. That was the plan. And yet, here we are. Something went wrong. Or, depending on how you look at it, something went right. At some point in the first fraction of a second after the Big Bang, the perfect balance broke. Just slightly. Just enough. For every 1 billion particles of antimatter, there were 1 billion and 1 particles of matter. A rounding error on the scale of existence. A blip. An anomaly so small it barely registers as a difference at all. The antimatter and the matter collided. All of it. A catastrophic mutual destruction that flooded the early universe with energy. And from that wreckage, from that single, solitary extra particle in every billion, everything you've ever seen or touched or loved was built. You are the leftover. The remainder. The 1 in a billion survivor of the greatest annihilation in history. And physics cannot explain why you exist. Before we go further, we need to talk about what antimatter actually is. Because the word sounds like science fiction, like something you'd find in a comic book next to faster-than-light travel and friendly aliens. But antimatter is real. We make it in laboratories. We've held it, briefly, carefully, in magnetic bottles, like trying to cup water in your hands without letting a single drop touch your skin, because the moment it does, both the water and your hand cease to exist. Here's the idea. Every particle in the universe has a twin. Not a copy, a mirror image. An electron, which carries a negative electric charge, has a twin called a positron, which carries a positive charge but is otherwise identical. Same mass. Same spin. Same everything, except the charge is flipped. A proton has an antiproton. A neutron has an antineutron. Even particles we don't think of as having charge have subtle quantum properties that get reversed in their antimatter counterparts. Think of it like this. Imagine you're looking at yourself in a mirror. The reflection looks exactly like you. Same face, same height, same shirt. But everything is flipped. Your right hand is now your left. The coffee mug in your right hand is now in your left. It's you, but reversed in a way that goes deeper than just the image. That's antimatter. A reversed version of normal matter, so fundamentally opposite that if the two of you ever made physical contact, you'd both vanish in a flash of pure energy. Now, here's what makes this unsettling. The laws of physics, when Paul Dirac first wrote down the equations for quantum mechanics in 1928, didn't just allow antimatter to exist. They demanded it. The math required it. Dirac found that for every solution describing a normal electron, there was an equal and opposite solution describing something else, something with the same mass but opposite charge. He initially thought he'd made an error. He tried to explain it away. But the math didn't care about his preferences. In 1932, Carl Anderson pointed a cloud chamber at cosmic rays streaming down from space and found exactly the particle Dirac's equations had predicted, the positron, the first confirmed piece of antimatter ever observed. The universe had been hiding it in plain sight. And once we knew it was real, once we knew the mirror had a reflection, The question stopped being does antimatter exist and became something far more disturbing. Why is there any matter left at all? Let's slow down for a second. Because to really feel the weight of this problem, to understand why physicists lose sleep over it, you need to understand what the universe was doing in its very first moments. And to do that, you need to understand a concept so elegant, so deeply baked into the foundation of physics, that breaking it feels almost like a crime. Symmetry. Not the artistic kind. Not the pleasing visual balance of a butterfly's wings or a cathedral's facade. Physics symmetry is something deeper. It's the idea that the laws of nature don't play favorites. That the universe runs on rules that are fair, impartial, the same everywhere, in every direction, for every participant. Here's a simple version. Drop a ball on Earth, it falls down. Drop a ball on the other side of the Earth, it also falls down, toward the center. The law of gravity doesn't care which way you're oriented. It applies equally. That's a symmetry. The law is the same regardless of your position. Now scale that up. One of the most important symmetries in particle physics is called CP symmetry. 2 letters. 2 transformations. Huge implications. C stands for charge conjugation, the operation where you swap every particle for its antimatter twin. Flip all the charges. Turn matter into antimatter. P stands for parity, the operation where you flip the spatial coordinates, like holding the universe up to a mirror. Left becomes right. North becomes south. CP symmetry says this: if you take any physical process, flip all the charges and mirror the spatial coordinates, the new process should be physically identical to the original. The laws of physics should be the same for matter as for antimatter. Everything should be symmetrical. Everything should be fair. And if that's true, if CP symmetry holds perfectly, then the Big Bang had absolutely no reason to produce more matter than antimatter. The same laws governed both. The same forces acted on both. In the same environment, under the same conditions, they should have been produced in exactly equal numbers. And then annihilated each other completely. Think about it like a coin factory. You build a machine that makes coins. But for every coin it stamps, the laws of physics, by symmetry, also require it to stamp one anti-coin. Same machine. Same laws. One coin, one anti-coin, every single time. You run the machine for the entire span of the early universe, producing particles at an incomprehensible rate, billions upon billions of them every microsecond. At the end, you count your coins. You have the same number of coins and anti-coins. You let them touch. They all annihilate. You're left with nothing. That's what CP symmetry predicts. That's what the equations demanded. A universe born in perfect balance and destroyed by that very perfection, leaving behind nothing but a thin, cold sea of photons drifting through an empty void forever. No second chances. No leftovers. No universe. And yet, here we are. Again. Still. Which means one of two things. Either CP symmetry isn't as perfect as we thought. Or there's some other mechanism we haven't found yet, working in the shadows, quietly tipping the scales. Either way, something cheated. And the story of how we figured that out is one of the strangest detective stories in the history of science. Before we catch the cheater, let's make sure we really understand what we're looking for. 1 in a billion. That's the number. That's the size of the imbalance that saved everything. For every billion antimatter particles produced in the Big Bang, there was one, just one, extra matter particle. The other billion pairs annihilated each other perfectly. And from that single leftover particle, multiplied across the incomprehensible scale of the early universe, everything was built. Let's try to feel that number, because a billion is one of those figures the human brain cheerfully ignores as very large without really processing it. A billion seconds ago was 1994. Bill Clinton was president. The Shawshank Redemption just came out. The internet was a novelty. That's how long a billion seconds takes to pass. And we're talking about a ratio of 1 to a billion, one extra particle for every billion pairs. Now imagine a stadium. Not a small one, a stadium that holds 1 billion people. Every single seat filled. You're looking out across this crowd and somewhere, in one seat, is one extra person. One seat that shouldn't be occupied. You can't see them from where you're standing. The crowd is so uniform, so perfectly matched, that this one extra person is statistically invisible. And yet, if you removed them, if that one person had never shown up, the stadium would be empty. Because everyone else would have found their perfect partner and left together. You are that person. Every atom in your body. Every star you've ever seen. Every galaxy in the observable universe, containing hundreds of billions of stars each, all of it traces back to that 1 in a billion surplus. To a cosmic accident so small it barely registered, and yet so consequential that without it, reality itself would not exist in any recognizable form. And here is the maddening part. We don't know where that extra person came from. We don't know why they showed up. We don't know what rule they broke to get into the stadium. We know they were there, we are the evidence, but we cannot find the mechanism that put them there. We cannot reproduce it in a laboratory. We cannot point to the equation and say, there. That's why. The universe left us its autobiography. But it tore out the most important page. That missing page has a name. Physicists call it baryogenesis, the origin of the matter-antimatter asymmetry that gave rise to the matter-dominated universe we live in today. And solving it is one of the deepest unsolved problems in all of physics. Not because we lack tools or intelligence, but because every time we think we've found the answer, the universe whispers back, not quite. Look deeper. So let's look deeper. Here's where physics gets genuinely strange. For a long time, most of the early 20th century, physicists believed CP symmetry was inviolable, unbreakable, a bedrock law, not a guideline, not a tendency, a rule so fundamental that the universe itself enforced it without exception. And why not? Everything they tested obeyed it. Electromagnetism, perfectly symmetric. The strong nuclear force, the force that holds the nucleus of every atom together, perfectly symmetric. Every experiment, every measurement, every collision in every particle accelerator pointed to the same answer: matter and antimatter behave identically under mirrored conditions. The coin factory makes perfect pairs, every time. There was even a famous theorem, the CPT theorem, which goes one step further. It says that if you apply charge conjugation, parity reversal, and time reversal, running the clock backwards, the laws of physics are absolutely, provably, without any known exception symmetric. CPT symmetry is believed to be exact. It's built into the mathematical structure of quantum field theory so deeply that violating it would require throwing out not just one equation, but the entire framework we use to understand particle physics. So if CPT is exact, if the full triple symmetry holds, then any violation of CP must be compensated by a corresponding violation of T, time reversal. Which opens its own philosophical rabbit hole. But we'll get there. The point is this: the community of physicists in the mid-20th century had very strong theoretical reasons to believe CP symmetry was real and absolute. It was one of nature's rules. Elegant. Clean. Fair. And then, in 1964, in a laboratory in New York, two physicists ran an experiment that should have been routine, a simple check, a confirmation, a box-ticking exercise. And they broke the universe. 1964. Brookhaven National Laboratory. Long Island, New York. Val Fitch and James Cronin were not trying to change physics. They were not chasing a Nobel Prize. They were not even particularly convinced they'd find anything interesting. They were running what was essentially a verification experiment, the scientific equivalent of double-checking your math on a problem everyone already agrees is solved. They were studying particles called kaons. Neutral kaons. Strange little things that physicists had been poking at for years, trying to understand the weak nuclear force, one of the four fundamental forces of nature, the one responsible for radioactive decay. Kaons are mesons. That means they're built from one quark and one antiquark, already a mixed household, matter and antimatter cohabiting in a single particle. They're unstable. They decay. And the way they decay was supposed to tell you something about CP symmetry. Here's the setup. Neutral kaons come in two flavors. One type, call it K-short, decays very quickly, in about 90 trillionths of a second. It decays into two pions. The other type, K-long, lives much longer, nearly 500 times longer, and decays into 3 pions. CP symmetry predicts that these two decay modes are distinct and exclusive. K-long decays into 3 pions. That's the rule. That's what the symmetry demands. Fitch and Cronin let their kaon beam travel far enough that all the K-short particles had already decayed. What remained should have been pure K-long. And K-long, by CP symmetry, should only decay into 3 pions. It was supposed to be a clean, boring confirmation. Instead, they found that roughly 1 in every 500 K-long particles was decaying into 2 pions. Not 3. 2. A small number. Easy to miss. Easy to dismiss as experimental error. But Fitch and Cronin were careful. They checked. They rechecked. They ruled out every mundane explanation they could think of. The signal was real. Kelong was doing something it wasn't supposed to do. It was violating CP symmetry, in a small way, in a quiet way, almost shyly, but it was violating it. The mirror wasn't perfect. There was a crack. The physics world reacted with a mixture of awe and deep unease. This wasn't just an anomaly in a single experiment. It was a rupture in something everyone had taken for granted as a foundation of reality. CP symmetry, the principle that matter and antimatter obey the same laws, was not exact. The universe did, in some small, measurable way, treat matter differently from antimatter. In 1980, Fitch and Cronin received the Nobel Prize in Physics for what they'd found. Because the implication was enormous and immediate. If CP symmetry could be violated, if the universe's laws were not perfectly fair to matter and antimatter, then suddenly there was a door. A possible mechanism. A loophole through which the Big Bang might have escaped its own symmetry and produced more matter than antimatter. For the first time, we had evidence that the universe was capable of cheating. The question was this enough cheating? Was this one crack in the mirror sufficient to explain the entire matter-dominated universe we live in? Could this tiny 1 in 500 asymmetry in kaon decay account for the 1 in a billion surplus that gave birth to everything? The answer, when physicists did the math, was both exciting and deflating. No. Not even close. The CP violation in kaon decay was real. But it was orders of magnitude too small to explain the observed matter-antimatter imbalance in the universe. It was a crack, but not a large enough crack to let everything through. It was a proof of concept, not a solution. Which meant the hunt wasn't over. It had barely begun. Let's sit with kaons for a moment longer, because they deserve it. They're strange in more ways than one. Strange is actually a technical term here, referring to a quantum property called strangeness, carried by the strange quark inside them. And the kaon's strangeness is precisely what made it such a useful laboratory for probing CP violation. Think of a kaon as a coin that can't decide what it is. A neutral kaon is in a constant state of quantum identity crisis. It oscillates, back and forth, continuously, between being a kaon and being an anti-kaon. Not flipping like a coin you toss in the air, where it's one or the other at any given moment. More like a coin that is genuinely, physically, simultaneously both heads and tails, and is oscillating between the two states in a quantum superposition, until you look at it and force it to choose. This oscillation happens billions of times per second. It's one of the most dramatic demonstrations of quantum weirdness in particle physics, a visible, measurable consequence of quantum mechanics operating at a scale we can actually detect. And here's where CP violation bites. If CP symmetry were perfect, if the laws were truly identical for matter and antimatter, then the kaon would oscillate perfectly symmetrically. Exactly equal time as a kaon, exactly equal time as an anti-kaon. A perfectly balanced quantum pendulum. But it doesn't. The oscillation is slightly asymmetric. The kaon spends fractionally more time as a kaon than as an anti-kaon. A tiny, almost imperceptible preference, but real. Measurable. Reproducible. The universe is showing a preference, however slight, for matter over antimatter. Not because someone programmed it that way. Not because of any external intervention. But because the laws themselves, at the quantum level, are subtly, fundamentally tilted. This is the thing that makes physicists both thrilled and frustrated. Thrilled because it means the asymmetry is built in. It's not a cosmic accident or an initial condition set by something outside physics. The tilt is in the equations themselves. The universe's preference for matter is structural. Frustrated because the tilt is nowhere near big enough. You need a 1 in a billion imbalance to explain the universe. Kaons give you something many orders of magnitude smaller. It's like trying to fill an ocean with a single leaking faucet. The mechanism exists. The direction is right. The scale is catastrophically wrong. So physicists did what physicists always do when one particle isn't enough. They found a bigger particle. Enter the B meson. If kaons were the opening act, the first sign that CP symmetry could crack, then B mesons were the main event. Heavier, more complex, and containing a bottom quark, another, heavier cousin of the strange quark, B mesons were predicted to show CP violation on a much larger scale than kaons. The theory said so. The math said so. And in the late 1990s and early 2000s, two of the most ambitious particle physics experiments ever built were designed specifically to find out. One was called BABAR, built at the Stanford Linear Accelerator Center in California. The other was called BEL, built at the KEK Laboratory in Japan. Both were what physicists call B factories, machines designed to produce B mesons in enormous quantities and study their decay patterns with extraordinary precision. Not because B mesons were practically useful. Not because anyone had a product in mind. But because B mesons were a window. A controlled, reproducible, laboratory-scale window into the same kind of asymmetry that, on a vastly larger scale, produced the universe. The experiments worked by colliding electrons and positrons, matter and antimatter, at carefully tuned energies to produce pairs of B mesons and anti-B mesons. Then they watched. With detectors the size of houses, bristling with sensors and electronics, recording every particle track, every energy deposit, every quantum fingerprint of decay. Billions of collisions. Years of data. Armies of physicists combing through the numbers. What they found confirmed the prediction. B mesons do violate CP symmetry. More dramatically than kaons. In some decay channels, the asymmetry between how often a B meson decays one way versus how often an anti-B meson decays the same way reaches levels of 10, 20, even 30%. Enormous by the standards of kaon physics. Both the BABAR and BEL teams announced their results in 2001. The CP violation in B mesons was real, it was large, and it was exactly the kind of thing the standard model of particle physics, the reigning theory of how all known particles and forces work, had predicted. And that last part is where the story gets complicated again. Because when physicists plugged the B meson results into the equations of baryogenesis, when they asked whether this level of CP violation, combined with the other known ingredients, was enough to produce the matter-dominated universe, the answer came back the same as before. Not enough. Still not enough. The standard model of particle physics, even with all its known CP violation included, from kaons, from B mesons, from everything, can explain only a tiny fraction of the observed matter-antimatter asymmetry in the universe. Some estimates suggest the standard model accounts for less than 1/billionth of the asymmetry we need. The machine exists. The mechanism is real. But it's running at a whisper when the universe needed a roar. Which means, and this is the part that keeps the lights on in theoretical physics departments around the world, there is almost certainly a source of CP violation that we haven't found yet. Physics beyond the standard model. New particles. New forces. New mechanisms that operated in the first moments of the universe and left an imprint too faint for our current tools to see, but not too faint to have made everything. The universe hid something. And we are only now beginning to understand how deep the hiding place goes. Let's zoom out. Because we've been following the experimental thread, kaons, B mesons, laboratories, detectors, and it's easy to get lost in the machinery and forget the enormous question sitting behind all of it. So let's come back to the core problem. Let's name it properly. Baryogenesis. Baryon is the technical term for the heavy particles, protons, neutrons, that make up atomic nuclei. The stuff that makes up you, and the Earth, and the Sun, and every visible structure in the universe. Baryogenesis is the process by which the early universe ended up with more baryons than antibaryons. More matter than antimatter. That 1 in a billion surplus that allowed everything to exist. And the problem, the deep, maddening, beautiful problem, is that we don't have a complete theory of how it happened. We know it happened. You are proof. But proof of the outcome is not an explanation of the mechanism. The crime scene exists. The victim is gone. But we haven't found the murder weapon, and our best suspect, the Standard Model, has a solid alibi for most of the scene. Now, there is a framework. A set of conditions. In 1967, a Soviet physicist named Andrei Sakharov, the same Sakharov who also built the Soviet hydrogen bomb and later became one of the most important human rights advocates in history, which is its own remarkable story, sat down and worked out what conditions the early universe must have satisfied in order for baryogenesis to occur. For the matter-antimatter balance to break. He found three conditions. All of them necessary. None of them sufficient on their own. They are now called the Sakharov conditions, and they are worth understanding, not just as physics, but as a kind of cosmic checklist. A list of requirements the universe had to meet in order to allow itself to exist. The first condition, baryon number violation. The universe needed a process that could change the total number of baryons, that could create more matter particles than antimatter particles, or destroy antimatter faster than matter. In physics, most interactions conserve what's called baryon number. A proton goes in, a proton comes out. You can't just create a proton from nothing. But Sakharov said, there must have been a time, or a mechanism, where this rule broke down. Where the accounting books of the universe were not balanced. Where you could, under the right conditions, create a baryon without creating a corresponding antibaryon. We actually have a candidate for this. In the Standard Model, there are processes called Sphaleron transitions, exotic, high-energy events that can violate baryon number and lepton number simultaneously. They're suppressed at normal temperatures, you'll never see one at room temperature, or even in a particle accelerator. But in the extreme heat of the early universe, fractions of a second after the Big Bang, sphalerons would have been common. Active. Constantly reshuffling the baryon ledger. So the first condition is likely met. Good start. The second condition, C and CP violation. This one we've already met. The laws of physics must treat matter and antimatter differently. C violation means the laws aren't the same when you swap particles for antiparticles. CP violation means they aren't the same even when you also flip the spatial mirror. We've seen CP violation. In kaons. In B mesons. It's real. It exists. But, and this is the critical qualifier, it has to be large enough. The amount of CP violation the universe deployed in its first moments had to be sufficient to tip the balance by 1 part in a billion. And as we've established, everything we've measured in the Standard Model falls dramatically short of that requirement. So the second condition is partially met. We have the mechanism. We don't have the magnitude. There must be more CP violation somewhere, in particles we haven't found, in processes we haven't observed, in an extension of the Standard Model that we haven't yet written down. The third condition, departure from thermal equilibrium. This one is the subtlest, and in some ways the most profound. If the early universe had been in perfect thermal equilibrium, if everything had been perfectly smooth, perfectly uniform, every reaction and its reverse proceeding at exactly the same rate, then any asymmetry generated by baryon violation and CP violation would have been immediately washed out. The universe would have thermalized its way back to zero. Equilibrium is the enemy of asymmetry. In a perfectly balanced, perfectly mixed system, information about which side was heavier gets erased. You need a non-equilibrium environment, a system that is cooling, changing, transitioning, for an asymmetry to survive long enough to become permanent. And the early universe was most definitely not in equilibrium. It was expanding, cooling rapidly, going through phase transitions, moments where the fundamental forces of nature were separating from each other, like water freezing into ice, where the smooth uniformity of liquid water suddenly breaks into the ordered crystalline structure of ice. These phase transitions are violent, non-equilibrium events. Bubble nucleation. Rapid symmetry breaking. The universe was churning. So the third condition is likely met. The early universe was far enough from equilibrium to allow an asymmetry to lock in. 3 conditions. 3 requirements for baryogenesis. And the verdict: 1 met comfortably. 1 met partially, and not nearly sufficiently. 1 met in principle, with significant caveats about the exact nature of the phase transition. Sakharov gave us the map. We've confirmed that the territory exists. But we're still missing a crucial piece of the route, the large-scale CP violation that would make the numbers work. And until we find it, the origin of the universe remains, technically, an open case. Here's what makes this problem genuinely haunting. It's not just that we're missing a mechanism. It's that the mechanism we're missing, whatever it is, operated in the first fractions of a second after the Big Bang, at energies we cannot recreate in any laboratory on Earth, possibly at energies we will never be able to recreate. The universe ran its most important experiment exactly once, at a scale and temperature that are forever beyond our direct reach. We are like forensic scientists called to a crime scene a billion years after the fact. The evidence has been diluted by cosmic expansion. The witnesses, the exotic particles that carried the original asymmetry, decayed long ago. The temperature at which everything happened was 10 million billion times hotter than the center of the sun. We're trying to reconstruct a single event that lasted less than a microsecond, from clues spread across the entire observable universe. And yet, this is the part that should fill you with something between admiration and vertigo: we are not helpless. We have tools. We have strategies. We have theories that make predictions we can test, even if we can't recreate the original event. Because the universe, despite destroying its most important evidence, left something behind that it couldn't destroy. It left us. And it left us with mathematics. With the ability to write down equations, follow their logic, and discover what they demand. Sakharov did this in 1967. Fitch and Cronin did this in 1964 with their detectors. The Babar and Bell collaborations did it at the turn of the millennium. Each time, we got a little closer. Each time, the universe gave us a little more of its secret. The next clue might already be in our hands. And it might come from the most ghostly, most elusive, most fundamentally weird particle in the entire Standard Model. A particle so light it was once thought to have no mass at all. A particle that passes through the entire Earth as if it isn't there, as if a planet-sized obstacle is barely an inconvenience. A particle that comes in 3 different personalities, and switches between them spontaneously, in mid-flight, without any obvious reason. A particle whose asymmetry, if it has one, might dwarf everything we've found in kaons and B-mesons combined. The neutrino. Let's talk about something that should not be able to matter. Right now, at this exact moment, approximately 100 trillion neutrinos are passing through your body. Every second. 100 trillion. They come from the sun, from cosmic rays, from the distant death screams of exploding stars in galaxies millions of light-years away. They arrive constantly, from every direction, at nearly the speed of light. And you feel nothing. Not because they're small, though they are, almost incomprehensibly so. Not because they're rare, they are in fact the second most abundant particle in the universe after photons. You feel nothing because neutrinos almost never interact with ordinary matter. They carry no electric charge. They're not affected by the strong nuclear force. The only forces they respond to are the weak nuclear force and gravity is so feeble at the scale of individual particles that it's essentially irrelevant. A neutrino can pass through a light-year of solid lead, a column of lead stretching from here to the nearest star, and have only a 50-50 chance of being stopped. They are, by any reasonable measure, the most antisocial particles in existence. And yet they might be the reason you exist. Here's the setup. In the Standard Model, neutrinos come in 3 types, called flavors. Electron neutrinos, muon neutrinos, and tau neutrinos. Named after the charged particles they're partnered with. For decades after their discovery, neutrinos were assumed to be massless, perfect little phantoms with no mass, traveling always at the speed of light, unchanging, featureless. Then, in 1998, the Super Kamiokande experiment in Japan, a tank of 50,000 tons of ultrapure water buried deep underground, lined with thousands of light sensors, watching for the rare flash of light that signals a neutrino interaction, made an announcement that rewrote the textbooks. Neutrinos have mass. Tiny, almost undetectable mass, but mass nonetheless. And more than that, neutrinos oscillate. They change flavor in flight. An electron neutrino produced in the Sun's core arrives at Earth as a mixture of all three flavors. It left as one thing. It arrived as something else. In between, it was in a quantum superposition of all three personalities simultaneously, and only the act of detection forced it to declare itself. This oscillation, this spontaneous identity shifting, is only possible if neutrinos have mass. And mass, in the context of particle physics, is never just a number. Mass is a clue. Mass is a connection to deeper structure. Mass implies a mechanism. And the mechanism that gives neutrinos their mass might be the hidden door behind the entire matter-antimatter mystery. The idea is called leptogenesis. And it is, in the opinion of many physicists, the most compelling solution to the baryogenesis problem currently on the table. Here's the chain of logic, laid out as simply as possible. We know from the Sakharov conditions that the universe needed CP violation to generate an asymmetry between matter and antimatter. We know the CP violation in the Standard Model, in quarks, in kaons, in B mesons, is nowhere near large enough. So either there's more CP violation in the quark sector that we haven't found yet, or the asymmetry didn't originate in the quark sector at all. Leptogenesis takes the second option. Leptons are the other family of fundamental particles, electrons, muons, tau, and their associated neutrinos. Not quarks. Not baryons. The other half of the matter family tree. Leptogenesis proposes that the original asymmetry, the 1 in a billion imbalance that saved the universe, was generated not in quarks but in leptons. Specifically, in the neutrino sector. And then, through the Sphaleron processes we mentioned earlier, those exotic high-energy events that can shuffle matter at extreme temperatures, the lepton asymmetry was converted into a baryon asymmetry. The asymmetry started in one sector and migrated to another. It's like a shell game played at the beginning of time. The original imbalance was hidden under the neutrino shell. By the time we look at the baryon shell, the protons and neutrons, the asymmetry has been moved, and we can't see where it came from. Here's the deeper structure. To give neutrinos their extremely small masses through the most natural mechanism, a beautiful piece of theory called the seesaw mechanism, you need to introduce a new type of particle. Heavy neutrinos. Sometimes called right-handed neutrinos. These are hypothetical particles that would have existed in the early universe at energies far beyond what any current accelerator can reach. They are not in the Standard Model. They are beyond it. But they are precisely the kind of new physics that the matter-antimatter problem seems to demand. The seesaw mechanism gets its name from a beautiful piece of arithmetic. Imagine a seesaw. On one side, you have a heavy object, the heavy neutrino, with a mass perhaps a billion times that of a proton. On the other side, an ordinary number. The seesaw tips under the weight of the heavy side, and the ordinary side rises to an unexpectedly tiny value. The observed neutrino mass, almost nothing, is the result of being on the light end of a seesaw balanced against something enormously heavy. The heavy neutrinos that anchor the seesaw would have been produced in huge numbers in the early universe. They would have been unstable, decaying quickly into lighter particles. And if their decays violated CP symmetry, if they decayed into matter and antimatter at slightly different rates, they would have seeded the universe with a lepton asymmetry. Which the sphalerons then converted into the baryon asymmetry. Which became U. The numbers, in this scenario, can actually work. Unlike the Standard Model CP violation in quarks, leptogenesis can in principle generate a large enough asymmetry to explain the observed universe. The heavy neutrino masses and couplings can be chosen, within theoretically reasonable ranges, to produce exactly the 1 in a billion surplus we need. This is not proof. Let's be absolutely clear about that. We have not observed heavy neutrinos. We have not directly detected leptogenesis. We cannot rewind the universe to its first microsecond and watch the process unfold. Leptogenesis is a framework, a beautiful, mathematically consistent, theoretically motivated framework that fits the evidence we have without contradicting anything we know. But it makes predictions. And one of those predictions is testable, right now, with experiments either running or under construction. If leptogenesis is real, if neutrinos are the hidden engine of the matter-antimatter asymmetry, then neutrinos, the light ones we can actually detect, should themselves violate CP symmetry. The decays of heavy neutrinos would have involved CP violation, and that same violation should show up, like an echo, in the oscillation behavior of ordinary neutrinos. Specifically, an electron neutrino oscillating into a muon neutrino should do so at a slightly different rate than an electron antineutrino oscillating into a muon antineutrino. Matter and antimatter behaving differently. CP violation in the neutrino sector. We are looking for this right now. The experiment is called nova neutrinos at the main injector. It shoots a beam of neutrinos from Fermilab, outside Chicago, to a detector in northern Minnesota, 810 kilometers away. By comparing how many electron neutrinos appear at the far end when you fire a neutrino beam versus an antineutrino beam, you can measure whether they oscillate differently. Whether CP symmetry is violated in the neutrino sector. The results so far are tantalizing. Suggestive. Not conclusive, not yet. The data shows a hint of asymmetry, a preference for one oscillation over another, at a level that is interesting but not yet statistically definitive. Not enough to claim a discovery. Enough to lean forward in your seat. There's also T2K in Japan, another long baseline neutrino oscillation experiment, which has reported similar hints. Their 2020 results, in particular, showed a preference for CP violation in neutrinos at a level that, if confirmed, would be deeply significant. And the next generation is coming. The Deep Underground Neutrino Experiment, DUNE, is under construction right now. A beam fired from Fermilab to a massive liquid argon detector buried 1.5 miles underground in South Dakota, 1,300 kilometers away. DUNE is designed with enough sensitivity to either confirm or rule out CP violation in neutrinos at a level that would be definitive. Not suggestive. Not tantalizing. Definitive. If DUNE finds CP violation in neutrinos, if the asymmetry is large enough and in the right direction, it will be the most important experimental result in particle physics in decades. It won't prove leptogenesis directly. The connection between low-energy neutrino CP violation and high-energy leptogenesis is model-dependent. It depends on the specific form of the heavy neutrino theory. But it will be a powerful, unprecedented piece of evidence pointing toward the neutrino sector as the origin of everything. And if DUNE finds nothing, if neutrino oscillations turn out to be perfectly CP symmetric, then leptogenesis in its simplest forms is in serious trouble. And we'll need to think harder. Look elsewhere. Go deeper into the unknown. Either way, the universe will have told us something. Either way, we will be closer to the page it tore out of its autobiography. There is a place at CERN, the enormous particle physics laboratory straddling the French-Swiss border near Geneva, where they make antimatter and keep it alive. Not for a nanosecond. Not for a microsecond. For minutes. For hours. It's called the Alpha experiment. And what they've managed to do there is, by any reasonable measure, one of the most technically extraordinary things human beings have ever accomplished. They take antiprotons, produced by slamming protons into a metal target at high energy and catching the antimatter debris, slow them down, cool them to temperatures just fractions of a degree above absolute zero, and combine them with positrons to form antihydrogen atoms. Complete antimatter atoms. The antimatter version of the simplest element in the periodic table. And then they hold them. In a magnetic bottle, a precisely shaped cage of magnetic fields that keeps the antihydrogen atoms suspended in vacuum, never touching the walls of the container, never touching anything made of normal matter. Because if they did, even a single atom of antihydrogen touching a single atom of the container wall, there would be a tiny flash of gamma radiation and both would be gone. Think about what that means. They are keeping the most reactive substance in the universe, a substance that annihilates on contact with literally everything around it, suspended in midair using nothing but magnetic fields. It's like storing fire in a soap bubble. Except the fire would destroy the soap bubble, the room, and the concept of soap bubbles if it ever made contact. And they do this not as a spectacle. Not as a demonstration of technical virtuosity, though it absolutely is that. They do it because they want to look at antihydrogen. To study it. To measure it with the same precision we've used to measure ordinary hydrogen, the most well-understood atom in physics, and compare the two. Because here is the question that sits underneath all the machinery and the magnetic bottles and the ultra-cold temperatures. Is antihydrogen exactly identical to hydrogen? Not just approximately. Not just close enough to confirm our theories. But exactly, precisely, to every measurable decimal place? If it is, if hydrogen and antihydrogen have exactly the same spectral lines, absorb and emit light at exactly the same frequencies, respond to gravity in exactly the same way, then CP symmetry is, at least at this level, intact. Matter and antimatter are perfect mirrors of each other in their atomic structure. And if they're not, if there's even a tiny, fractional difference in how antihydrogen behaves compared to hydrogen, then we've found something new. Something outside the standard model. Something that could point toward the deeper asymmetry that made the universe possible. The tool physicists use to compare hydrogen and antihydrogen is called spectroscopy. Here's the idea. An atom of hydrogen, one proton, one electron, can absorb light at very specific frequencies. Think of it as the atom's fingerprint. Its unique musical note. When you shine light on hydrogen, it absorbs certain wavelengths and ignores others. The frequencies it absorbs correspond to specific energy transitions, the electron jumping from one energy level to another, absorbing a photon of precisely the right energy to make the leap. These frequencies are known to extraordinary precision. The 1s, 2s transition in hydrogen, a particularly important one, where the electron jumps from its ground state to a specific excited state, has been measured to better than 15 decimal places. It is one of the most precisely measured quantities in all of science. A number known so accurately that if you wrote it on a piece of paper and then moved to the other side of the planet, the value would still be correct to within the width of a human hair compared to the length of a football field. If antihydrogen has even a fractional difference in its equivalent transition frequency, a difference at the 12th, 13th, 14th decimal place, Alpha's instruments might catch it. In 2022, the Alpha collaboration announced their most precise comparison yet. The 1s, 2s transition frequency in antihydrogen, measured and compared to hydrogen, agreed to a precision of about 16 parts per trillion. No difference detected. Matter and antimatter, at this level of measurement, appear identical. But, and this matters enormously, no difference detected does not mean no difference exists. It means no difference larger than our current experimental sensitivity. The universe might be hiding its asymmetry below the threshold of our instruments. And each generation of experiment pushes that threshold lower. Each generation asks a more precise question. The next question Alpha is asking, one that has never been answered before in the history of physics, is perhaps the most viscerally satisfying one. Does antimatter fall down? This question sounds almost comedic. Of course things fall down. That's what gravity does. It pulls. Everything with mass falls toward the source of gravity. An apple. A planet. A photon, light itself, bends around massive objects. Why would antimatter be any different? Here's why the question is serious. General relativity, Einstein's theory of gravity, is built on the equivalence principle. The idea that gravitational mass and inertial mass are the same thing. That the gravity an object feels is exactly proportional to the object's resistance to acceleration. This equivalence has been tested with extraordinary precision for normal matter. For electrons, for protons, for neutrons, and the atoms they compose. It holds, exactly, to the best of our measurement ability. But it has never been tested for antimatter. Not directly. Not in a clean, controlled experiment where you take a piece of antimatter and watch it fall. And there are theoretical reasons, not mainstream ones, but legitimate ones explored in certain extensions of the Standard Model, to wonder whether antimatter might respond to gravity differently than matter. Not necessarily falling up, but perhaps falling with a slightly different acceleration. Perhaps feeling gravity with a slightly different effective strength. In most extensions of physics, antimatter falls exactly like matter. The CPT theorem, if it holds exactly, essentially guarantees this, because the gravitational mass of an antiparticle is fixed by its inertial mass, which is fixed by CPT symmetry to be identical to the corresponding particle. So testing whether antimatter falls differently is, in a deep sense, a test of CPT itself. In 2023, the AlphaG experiment, a vertical version of the ALPHA apparatus, specifically designed to measure the gravitational behavior of antihydrogen, released their first results. They released antihydrogen atoms from their magnetic trap and watched which direction they drifted. The result: antihydrogen falls down. In the direction of the Earth. With a gravitational acceleration consistent, within the precision of the measurement, with ordinary matter. No antigravity. No upward drift. Antimatter, at least at this level of measurement, appears to fall the same way everything else does. And yet, the precision of that first measurement was only about 10%. Which means antimatter could still be falling with up to 10% more or less acceleration than normal matter, and the experiment wouldn't have caught it. Follow-up experiments, with much tighter constraints, are underway. The universe is being patient with us. It's letting us ask the question. It's just not giving away the answer cheaply. Let's step back from the laboratory. Way back. If there really is a symmetry between matter and antimatter, if, despite all the CP violation we've found, the universe at some larger scale maintains a balance, then there is a radical possibility that physics has not entirely ruled out. Somewhere out there, there might be antimatter galaxies. Not a galaxy made of exotic, fictional substance. A real galaxy. Stars and planets and nebulae and, possibly, life. But made of antimatter instead of matter. Antiprotons in the nuclei. Positrons in the orbits. Anti-carbon, anti-nitrogen, anti-water. Everything that a normal galaxy has, but flipped at the particle level. If the universe had, for some reason, separated into antimatter regions and matter regions early in its history, if the two domains were far enough apart that they hadn't collided yet, then both could persist. The annihilation would happen only at the boundaries, at the edges where matter and antimatter regions meet, and it would produce a distinctive signal, a haze of gamma radiation at a very specific energy, 511 keV, the energy released when an electron and a positron annihilate, glowing along the cosmic boundary like the edge of a war. We have looked for this. We have searched the sky for the telltale glow. And we have found no evidence of large-scale antimatter domains. No antimatter galaxies. No annihilation boundaries. The gamma-ray sky, while complex and fascinating, does not show the signature of matter-antimatter domain walls on cosmic scales. Which tells us something important. The asymmetry wasn't just local. Wasn't just our corner of the universe that got lucky. The imbalance appears to be universal, the same everywhere, in every direction, at every scale we can observe. Whatever produced the 1 in a billion surplus did so uniformly, simultaneously, across the entire observable universe. That's 13 billion light-years in every direction. A volume of space so large that the word enormous doesn't even begin to reach it. That kind of uniform, universe-wide asymmetry doesn't happen by accident. It doesn't happen because matter happened to cluster here while antimatter clustered somewhere else. It requires a mechanism that operated everywhere at once, in the first fraction of a second, when the universe was small enough that every region was in causal contact with every other region, and a single process could set the same initial conditions across everything. That mechanism, whatever it was, is the deepest mystery in cosmology. And it happened once. In a window of time so brief, at an energy so extreme, that it left almost no direct trace. Almost. There was a moment, a specific, datable, physically describable moment, when the universe fundamentally changed what it was. Not what it contained. What it was. This moment happened approximately 100 billionth of a second after the Big Bang. The universe was roughly the size of a marble, though that comparison understates how much matter and energy was crammed into that marble, because it was everything. The temperature was 10 million billion degrees. And something happened that physicists call the electroweak phase transition. To understand why it matters, you need to understand what came before it. In the first instance after the Big Bang, the four fundamental forces of nature were not four separate things. They were unified. The electromagnetic force, the one that governs light, electricity, and the behavior of charged particles, and the weak nuclear force, the one responsible for radioactive decay, and for the CP violation we've been discussing, were a single, unified force. The electroweak force. One unified interaction. One set of symmetries. No distinction between electromagnetism and the weak force because the universe was too hot for any distinction to survive. At that temperature, all the force-carrying particles, the photon, the W bosons, the Z boson, were massless. They all traveled at the speed of light. They were, in a mathematical sense, interchangeable components of the same underlying symmetry. And then the universe cooled. Crossed a critical temperature. And something switched. The Higgs field, a quantum field that permeates all of space, the field associated with the Higgs boson discovered at CERN in 2012, underwent what physicists call spontaneous symmetry breaking. Above the critical temperature, the Higgs field sat in a symmetric state, the same in every direction, like a ball balanced at the top of a hill. Below the critical temperature, that balance became unstable. The ball rolled off the hill and settled into a new, lower energy state, a specific value, a specific direction in the abstract mathematical space of the theory. This is the moment the universe changed shape. Not physically, space itself didn't rearrange. But the mathematical landscape of physics reorganized. The electroweak symmetry broke. The single unified force split into two, electromagnetism and the weak force. The W and Z bosons acquired mass, becoming the heavy, slow, short-range particles they are today. The photon remained massless, the lone traveler still moving at the speed of light. And the Higgs field, now sitting in its new value, gave mass to every particle that interacted with it. Electrons. Quarks. All the building blocks of matter acquired their masses in this single moment, as if the universe had suddenly thickened, like water freezing into ice, and every particle swimming through it suddenly felt the drag. Now, why does this matter for antimatter? Because the electroweak phase transition is, by the Sakharov conditions, a prime candidate for the moment of baryogenesis. It happened at the right time. It was a dramatic departure from thermal equilibrium. It involved the forces, specifically the weak force, that we know can violate CP symmetry. And crucially, the Sphaleron processes we discussed earlier, those exotic baryon number violating events, were at their most active precisely around this transition temperature. The picture many physicists drew, through the 1980s and into the 1990s, was electroweak baryogenesis. The idea that as the Higgs field settled into its new value, it didn't do so uniformly across the universe. Instead, it nucleated. Bubbles of broken symmetry formed and expanded through the still symmetric background, like bubbles of ice forming in supercooled water. And at the walls of those expanding bubbles, where the broken and unbroken phases met, CP-violating processes could produce a local excess of baryons over antibaryons. Matter over antimatter, generated at the bubble wall, swept into the interior of the bubble before the sphalerons could wash it away. It is a beautiful picture. Elegant. Physically intuitive. Grounded in established theory. And then the Higgs boson was discovered at CERN in 2012. Its mass, 125 GeV, was precisely measured. And that measurement delivered a quiet but devastating verdict on electroweak baryogenesis in its simplest form. The problem is the nature of the electroweak phase transition. For electroweak baryogenesis to work, for bubble nucleation at the electroweak transition to generate enough baryon asymmetry, the transition needs to be what physicists call a first-order phase transition. Sharp. Dramatic. Like water freezing. A sudden jump from one phase to another, with a clear boundary between the two phases, a latent heat, and genuine bubble nucleation. If instead the transition is second-order, a smooth, gradual crossover, like water becoming less and less dense as it cools, with no dramatic jump, no sharp boundary, no latent heat, then the bubble walls disappear. The mechanism doesn't work. You can't generate a baryon asymmetry at a wall that doesn't exist. The mass of the Higgs boson determines which type of transition the electroweak phase transition was. The calculations are clear. If the Higgs were light enough, below about 70 GeV, the transition would have been first order. Dramatic. Bubbles. Baryogenesis possible. The Higgs is 125 GeV. At 125 GeV, the standard model electroweak phase transition is not first order. It is a smooth crossover. No bubbles. No walls. No mechanism for baryogenesis. The Higgs boson's discovery, one of the greatest triumphs of experimental physics in the 21st century, the confirmation of a particle predicted nearly 50 years earlier, the completion of the Standard Model, simultaneously ruled out the simplest and most elegant version of electroweak baryogenesis. The universe gave us the answer to one question and used it to close the door on another. But, and here is where physics refuses to give up, the Standard Model Higgs is not the only possible Higgs. Extensions of the Standard Model that are well motivated for other reasons often include additional Higgs bosons. Two Higgs doublet models. Supersymmetric theories, which require at least two Higgs doublets and predict a whole family of additional scalar particles. In these extended theories, the electroweak phase transition can be strongly first-order, even with the observed Higgs at 125 GeV. The additional particles change the shape of the energy landscape. They put the ball back on the hill. They restore the bubble nucleation. Which means electroweak baryogenesis is not dead. It is simply waiting for evidence of new physics beyond the Standard Model, specifically, evidence of additional Higgs bosons, or of particles that interact with the Higgs sector in new ways. And that evidence, if it exists, might already be within reach of the Large Hadron Collider. Or its successor. Or a future lepton collider. Machines either running now or being planned, designed explicitly to probe the Higgs sector with enough precision to see the fingerprints of additional scalars. The Higgs boson, in other words, is not just the final piece of the Standard Model. It might be the key to what lies beyond it. The particle whose properties encode the answer to baryogenesis, if we can measure them precisely enough. Here is a map of where we are. Imagine a ladder. Each rung represents an energy scale, a temperature at which certain physical processes operate. At the bottom of the ladder, room temperature. Normal physics. Atoms. Chemistry. Life. Going up, the temperatures inside particle accelerators, billions of degrees, energies where protons can be split apart and their quark constituents briefly set free. Higher still, the temperature of the electroweak phase transition, 10 million billion degrees. The moment the Higgs field switched on. The moment electroweak symmetry broke. The moment where electroweak baryogenesis would have operated, if it operated. Higher again, temperatures we cannot recreate in any laboratory on Earth, may never be able to recreate. The GUT scale, the energy at which the remaining three forces unify into one. Grand unified theories predict that at this energy, baryon number is no longer conserved. Protons can decay. Matter can transform into antimatter and back. Leptogenesis and its heavy neutrinos likely operated at energies somewhere near here, far above the electroweak scale, in a regime we can probe only through its low-energy echoes. And at the very top of the ladder, the Planck scale, 20 orders of magnitude above the electroweak transition, the point where gravity itself becomes quantum, where space and time lose their familiar meaning, where our current theories of physics break down entirely and we have no reliable description of what was happening. The Big Bang started at the top of this ladder and slid rapidly down it, cooling as the universe expanded. Baryogenesis happened at some rung along the way. We don't know which one. We can probe certain rungs with our accelerators. We can read the echoes of higher rungs in neutrino behavior, in cosmological observations, in the precise properties of the Higgs. But the full ladder remains unmapped. This is not a confession of failure. This is an honest accounting of where we are in one of the most ambitious scientific projects in human history, the project of understanding, from first principles, why anything exists. We have climbed several rungs. We can see the shape of the rungs above. We have tools being built right now that will let us reach higher. And the view from where we stand, the sheer scale of what we've already understood, is extraordinary. But the top of the ladder is still in the clouds. Let's stop the science for a moment. Not because the science is finished, it isn't, not even close. But because there's something happening underneath all these numbers and experiments and phase transitions that deserves to be named directly. Something that tends to get buried under the technical language, under the precision and the methodology, under the careful, cautious speech of people who spend their lives being rigorous. Something almost unbearable in its implications. You are not supposed to be here. Not in the motivational poster sense of, you beat the odds. Not in the 1 in a million sperm cell sense of biological improbability. Those are real, and they're interesting, but they're the wrong scale. We're talking about something so far beneath those comparisons that comparing them feels almost insulting to the strangeness of the truth. The universe, in its first fraction of a second, attempted to erase itself. Completely. Thoroughly. By its own internal logic. By its own symmetry. It created everything, and then, bound by the same laws that created it, it destroyed everything. It was a perfect, automatic, built-in annihilation. Not a catastrophe. A consequence. The natural outcome of a symmetric universe doing exactly what a symmetric universe does. And it almost worked. 13.8 billion years later, sitting in whatever room you're in right now, you are the residue of that almost. The thin, improbable layer of matter that survived because the cancellation wasn't quite complete. Because somewhere, in the churning, incomprehensible violence of the first microsecond, something flinched. Some law bent. Some symmetry cracked by just enough, 1 part in a billion, to leave a remainder. And from that remainder, from those leftover particles, those survivors of a war that annihilated literally everything else, the universe built everything. Hydrogen. Helium. Stars. Carbon. Oceans. Cells. You. All of human history. Every thought ever thought. Every song ever written. Every love ever felt. Every question ever asked. Including this one. Think about that chain. The matter-antimatter asymmetry didn't just produce the physical substrate of the universe. It produced the possibility of curiosity. It produced beings capable of noticing that they exist, wondering why, and spending careers and lifetimes and enormous amounts of money building machines to find out. The 1 in a billion surplus didn't just save matter. It eventually, after billions of years of stellar evolution and planetary chemistry and biological complexity, produced the very minds that are now trying to understand why it happened. The universe created its own investigators. From its own accident. There is something in that fact that resists easy description. It sits somewhere between profound and vertiginous. Between awe and absurdity. You can choose to find it humbling, that we are the accidental remainder of a self-destruction. Or you can find it extraordinary, that the remainder turned out to be capable of understanding its own origin. Both feelings are justified. Both are appropriate responses to something this strange. What's not appropriate, what the physics simply will not support, is indifference. This is not a detail. This is the detail. The most fundamental fact about the universe you inhabit is that it almost wasn't one. Here is something that doesn't get discussed enough. When matter and antimatter annihilated in the first second, when that billion-to-one massacre played out across the early universe, what became of the antimatter? Not philosophically. Physically. What happened to it? It became light. Every annihilation event, every matter-antimatter pair that collided and destroyed each other, released their combined energy as photons. Gamma rays. Pure electromagnetic radiation, carrying no mass, building nothing, interacting only weakly with what little matter remained. The early universe was flooded with this radiation, a blinding, all-encompassing sea of light, far more intense than anything that exists today, the afterglow of the greatest destruction in history. As the universe expanded and cooled, this radiation stretched. The high-energy gamma rays became lower-energy X-rays. Then ultraviolet. Then visible light. Then infrared. Then microwave radiation. Cooling, redshifting, losing energy to the expansion of space itself. Spreading out across the growing universe, thinning, dimming, but never quite disappearing. And today, right now, that radiation still exists. It's called the cosmic microwave background. The CMB. A faint, cool bath of microwave radiation that fills the entire universe uniformly in every direction. When you tune an old television set to a channel that doesn't broadcast, when you see the static, the white noise, about 1% of that static is CMB photons hitting your antenna. Ancient light. 13 billion-year-old light. The literal afterglow of the matter-antimatter annihilation that happened in the first second of the universe. The antimatter didn't disappear. It transformed into light that is still traveling, still filling space, still arriving at your television antenna, right now. The antimatter became the background of everything. The cosmic wallpaper. The faint, cold, omnipresent echo of the catastrophe that almost erased everything. There is something haunting about that. The antimatter, the mirror image of everything you're made of, the substance that was produced alongside matter in equal amounts and was meant to be its perfect partner, is still here. Not as particles. Not as structure. But as the background hum of the universe. Dispersed, cold, stretched across 13 billion light-years of space. The ghost of the half of creation that didn't make it. Every photon in the CMB is a tombstone. And together they tile the entire sky. The cosmic microwave background is not just poetic. It is one of the most scientifically valuable objects in existence. Because it is a snapshot. A photograph of the universe at a very specific age, approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms for the first time. Before this moment, the universe was a hot, dense plasma, opaque, like the interior of a star, with photons bouncing around too rapidly to travel freely. After this moment, called recombination, the photons were released. They streamed freely through space for the first time, carrying with them an imprint of the universe's structure at that exact moment. That imprint is the CMB we observe today. Cooled to just 2.7 degrees above absolute zero. But still carrying its ancient information, encoded in the precise temperature fluctuations across the sky, variations of about 1 part in 100,000 in the CMB temperature from one point in the sky to another. These fluctuations are not random. They are the fossil record of quantum fluctuations in the very early universe, tiny quantum jitters in the density of matter that, over hundreds of millions of years, grew under gravity into the large-scale structure we see today. Filaments. Galaxy clusters. Superclusters. The cosmic web of structure that spans billions of light-years, all traced back to quantum noise in the first fraction of a second. And the CMB tells us something critical about the matter-antimatter asymmetry. By measuring the precise ratios of hydrogen to helium to deuterium in the early universe, ratios preserved in the CMB and in the abundances of light elements we observe today, physicists can calculate exactly how many baryons per photon existed in the early universe. The baryon-to-photon ratio. A single number that encodes the result of baryogenesis, the surviving fraction of matter after the annihilation. That number is approximately 6 times 10 to the power of minus 10. 6 in 10 billion. The 1 in a billion number we've been discussing, refined to a precise measurement. Not a rough estimate. An actual, measured quantity, extracted from the oldest light in the universe. This is remarkable. We know the exact size of the imbalance that saved everything. We can measure it. We can calculate what it should produce, and our calculations match what we observe, everywhere we look, to extraordinary precision. The abundance of hydrogen. The amount of helium. The tiny traces of lithium and deuterium. All consistent with a single baryon per approximately 2 billion photons at the end of baryogenesis. The universe left us the answer to the "how much" question written in its oldest light. What it hasn't told us, what remains stubbornly, frustratingly silent, is the answer to the how and why. The mechanism. The physics. The deeper law that tilted the balance. We know the size of the miracle. We just don't know what performed it. Let's use a different frame for a moment. Imagine you're a detective. You arrive at a crime scene, but not a normal one. This crime scene is 13 billion years old. The evidence has been diluted by cosmic expansion, scrambled by gravitational evolution, stretched and cooled and smeared across the entire observable universe. The perpetrator, the process that violated the cosmic symmetry and produced the matter surplus, left the scene before the universe was a microsecond old. And the only witnesses are particles that have been decaying, oscillating, and transforming ever since. What you have is this. A precise measurement of the outcome, 6 in 10 billion. A theoretical framework, the Sakharov conditions, that tells you what the crime required. Fragments of the mechanism, CP violation in kaons and B mesons, too small to be the full story, but unmistakably real. Hints of a larger violation, in neutrino oscillations, tantalizing but unconfirmed. A weapon that was certainly involved, the Sphaleron processes, but whose precise role is unclear. And a crime scene, the electroweak phase transition, that has been partially wiped clean by the discovery of the Higgs mass. Every good detective story has a moment where the detective almost gives up, where the leads run cold, where the evidence seems insufficient, where the case looks, for a moment, unsolvable. Physics had that moment in the 1990s. When the precision measurements of the CMB showed that the Standard Model's CP violation was catastrophically insufficient. When the kaon and B meson results confirmed the violation was real but not nearly large enough. When the Higgs mass closed the door on the simplest version of electroweak baryogenesis. For a while, baryogenesis looked like a cold case. And then new leads appeared. New witnesses stepped forward. The neutrino sector, previously thought to be nearly irrelevant to the matter-antimatter question, revealed hidden depths. Heavy neutrinos, demanded by the seesaw mechanism, offered a whole new theater for CP violation at energies far above anything the Standard Model predicted. Leptogenesis opened a new avenue. New experimental tools, Dune, Alpha, a next-generation collider, offered new ways to interrogate the universe. The case isn't cold. It never was. It's just harder than anything we've ever tried to solve. And the answer, when we find it, will not just be a number in a physics paper. It will be the deepest fact we have ever learned about reality. The explanation for why anything exists at all. The final answer to the oldest question a sentient universe has ever asked itself. Why am I here? Here is an uncomfortable truth about modern physics. The Standard Model, the theory that describes all known particles and 3 of the 4 fundamental forces, is almost certainly incomplete. Not wrong, exactly. It makes predictions of extraordinary precision. The magnetic moment of the electron, predicted by quantum electrodynamics to 11 decimal places and confirmed by experiment to 11 decimal places, is the most precisely tested prediction in the history of science. The Standard Model works spectacularly, reliably, across an enormous range of energies and conditions. But it has holes, gaps, places where it goes quiet and offers nothing. It doesn't include gravity. It doesn't explain dark matter, the invisible substance that outweighs visible matter in the universe by a factor of 5, and whose gravitational effects we can measure everywhere but whose particle identity we don't know. It doesn't explain dark energy, the mysterious pressure driving the accelerating expansion of the universe. And it doesn't explain baryogenesis. It cannot, within its own structure, produce enough CP violation to account for the matter-dominated universe we live in. These are not minor gaps. They are fundamental. And they all point in the same direction, toward physics beyond the standard model. New particles. New forces. New symmetries. A deeper theory, of which the standard model is a low-energy approximation, the way Newtonian mechanics is a low-energy approximation of special relativity. The most extensively developed candidate for that deeper theory is supersymmetry. SUSY, as physicists call it with affectionate informality. The idea that every particle in the standard model has a superpartner, a partner particle with the same quantum numbers but differing by half a unit of spin. The partners of the quarks are called squarks. The partners of the leptons are called sleptons. The partner of the photon is the photino. The partner of the Higgs is the Higgsino. Supersymmetry is beautiful mathematically. It solves, in one elegant stroke, several problems that plague the standard model, including a technical problem called the hierarchy problem, which asks why the Higgs boson is so much lighter than the Planck scale when quantum corrections should, by rights, push its mass up by 17 orders of magnitude. In supersymmetry, the quantum corrections from standard model particles are exactly cancelled by equal and opposite corrections from their superpartners. The Higgs mass is stabilized. The hierarchy is explained. And supersymmetry, crucially, provides new sources of CP violation. The superpartners, squarks, sleptons, neutralinos, can mix with each other in ways that introduce new complex phases into the theory. New angles in the mathematical space of the theory. New opportunities for the laws to treat matter and antimatter differently. In the minimal supersymmetric extension of the standard model, there are not one but dozens of new CP violating parameters, a vast new landscape of possible asymmetries, any one of which might be large enough to drive baryogenesis. There is one problem. We haven't found any superpartners. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, the machine that smashes protons together at 14 trillion electron volts and watches what comes out, has been running since 2008. It discovered the Higgs boson in 2012. And since then, it has searched exhaustively for supersymmetric particles. Squarks. Gluinos. Neutralinos. Every signature that supersymmetry predicts, in every corner of the parameter space that was theoretically most natural. Nothing. Not a single superpartner has been observed. The simplest, most natural versions of supersymmetry, the ones that physicists had the highest hopes for, are now ruled out by LHC data. The superpartners, if they exist, are heavier than the LHC can reach. Or they interact in ways that make them harder to detect than predicted. Or, the possibility that physicists find most uncomfortable, they simply don't exist. Supersymmetry is not dead. There are corners of supersymmetric theory that the LHC hasn't fully explored. Future colliders with higher energies might find what the LHC couldn't. But the easy, natural, obvious versions of supersymmetry, the ones that solved everything cleanly, are in serious tension with the data. And so the beyond standard model landscape has diversified. Theorists haven't abandoned the search for new physics. They've spread out, explored more territory, considered more possibilities. If supersymmetry isn't the answer, or isn't the complete answer, then what else is out there? The honest answer is, a lot. Perhaps too much. Extra dimensions. The idea, developed seriously in theories like those of Randall and Sundrum, that space has more than 3 dimensions, compact extra dimensions, curled up so tightly that we can't detect them directly, but whose presence modifies the behavior of particles and forces in ways that could show up in collider experiments. Extra dimensions naturally introduce new particles, Kaluza-Klein towers of excitations, one for each standard model particle at each level of the extra-dimensional spectrum. These new particles bring new CP-violating interactions. Technicolor and composite Higgs models. The idea that the Higgs boson is not a fundamental particle but a composite one, built from new, strongly interacting constituents, the way protons are built from quarks. In these theories, the electroweak phase transition can be strongly first-order, exactly what electroweak baryogenesis needs. The composite structure of the Higgs changes the shape of the energy landscape, puts the ball back on the hill, allows bubble nucleation. Axions. Originally proposed to solve a completely different problem, the strong CP problem, a separate mystery about why the strong nuclear force doesn't violate CP symmetry even though the mathematics of the theory allows it to. Axions are extremely light, extremely weakly interacting particles that might also constitute dark matter. Their cosmological evolution in the early universe could, in certain scenarios, play a role in baryogenesis. Dark photons. Mirror matter. Clockwork theories. Twin Higgs models. The theoretical landscape beyond the standard model is vast and rich and, if we're honest, somewhat bewildering. There are more proposed solutions than there are experiments to test them. This abundance is sometimes taken as a sign of desperation. Of theoretical physics untethered from experiment, spinning elaborate stories with no empirical anchor. And that criticism has some merit. The post-LHC era has forced a genuine reckoning in the particle physics community about which theories are truly predictive and which are merely consistent with existing data. But there is another way to read the landscape. The fact that so many different theoretical extensions of the standard model, developed for entirely different reasons, to solve entirely different problems, all naturally include new sources of CP violation, all naturally modify the electroweak phase transition, all naturally create pathways to baryogenesis. That convergence is telling us something. The physics beyond the standard model, whatever its specific form, almost certainly contains the ingredients for baryogenesis. The universe's preference for matter is not an isolated mystery. It is connected, deeply, structurally connected, to the other open questions in physics. Dark matter. The hierarchy problem. The strong CP problem. Neutrino masses. These are not separate puzzles with separate solutions. They may be different faces of a single, deeper theory that we haven't yet written down. The matter-antimatter asymmetry is not just one problem among many. It may be the thread that, when pulled, unravels the entire sweater and reveals what's underneath. While theorists argue and explore, experimentalists are building. The next generation of particle physics experiments is extraordinary in its ambition. Not just Dune, chasing neutrino CP violation in the American Midwest. Not just AlphaG, watching antihydrogen fall. There is a global, coordinated push, across multiple countries, multiple continents, multiple generations of physicists, to find the missing piece of the baryogenesis puzzle. At CERN, the high-luminosity LHC is being upgraded. Not to reach higher energies, but to produce vastly more collisions per second, giving experimentalists a much larger dataset to search for rare processes. CP violation in beauty hadrons, the family of particles containing bottom quarks, will be measured with unprecedented precision by the upgraded LHCb detector. Even small deviations from standard model predictions could be the fingerprints of new physics. Beyond the LHC, there are proposals for entirely new machines. The Future Circular Collider, FCC, a proposed 91-kilometer ring under the Swiss and French countryside, far larger than the LHC's 27-kilometer circumference. Its first phase would be an electron-positron collider, a precision machine for studying the Higgs boson with extraordinary accuracy, measuring its couplings to all other particles at the fraction of a percent level, looking for subtle deviations from standard model predictions that might signal composite structure, extra dimensions, or new heavy particles mixing with the Higgs. In China, the Circular Electron-Positron Collider, CEPC, is proposed with similar goals. In Japan, the International Linear Collider, ILC, represents a different approach, a straight-line electron-positron machine optimized for Higgs precision measurements at a fixed energy. And separately, there's the search for the neutron electric dipole moment, the NEDM. This is perhaps the most direct, targeted probe of CP violation beyond the standard model available to us. The neutron, a neutral particle built from quarks, should, if CP symmetry were exact, have no electric dipole moment. No separation of positive and negative charge inside it, no preferred direction for its internal charge distribution. If CP symmetry is violated by new physics, however, by the interactions of new particles beyond the standard model, the neutron should acquire a tiny, measurable electric dipole moment. A minuscule separation of its internal charges, pointing along its spin axis. Current experiments have measured the neutron EDM to be smaller than about 1.8 times 10 to the minus 26 electron centimeters. An almost inconceivably small number. And it's still consistent with zero. We haven't found one yet. But the next generation of NEDM experiments, including N2-EDM at PSI in Switzerland and Toucan at Triumph in Canada, aim to improve the sensitivity by another factor of 100. 100 times more sensitive. Reaching into a regime where many extensions of the standard model, if they generate the CP violation needed for baryogenesis, must leave a signal. Not might. Must. If certain classes of new physics are responsible for the matter-antimatter asymmetry, the next generation of NEDM experiments will see it. Or they won't. And that absence will be its own powerful message, ruling out entire categories of theory, narrowing the search, forcing physics to look elsewhere. Either way, we are not standing still. We are not waiting passively for the universe to reveal itself. We are building machines specifically designed to ask the universe the hardest question it has ever been asked, in the most direct language we know how to speak. Why is there something instead of nothing? There is an answer to the matter-antimatter problem that some physicists find deeply satisfying and others find deeply troubling. It doesn't require new particles. It doesn't require new forces. It doesn't require us to find anything in any laboratory. It requires only that we accept a single, enormous, philosophically loaded premise. That our universe is not the only one. The idea is the multiverse. Not in the science fiction sense, not parallel universes where you made different choices, where history branched at critical moments, where a version of you became a concert pianist. The cosmological multiverse. The idea, emerging naturally from the mathematics of eternal inflation, the leading theory of what happened before and during the Big Bang, that our universe is one bubble in an infinite, ever-expanding foam of universes. Each bubble nucleating out of a quantum fluctuation in an eternally inflating background. Each bubble potentially having different physical constants, different symmetry-breaking patterns, different low-energy physics. In this picture, the number of universes is not just large. It is, in a mathematically meaningful sense, infinite. Every possible configuration of physical law that is consistent with the underlying framework is realized somewhere. Most of these universes are hostile to structure, the constants are wrong, the forces are mistuned, atoms don't form or stars don't ignite or galaxies collapse before chemistry can happen. But some, a tiny fraction, happen to have the right conditions for complexity. For life. For beings capable of asking why they exist. And here is where it connects to baryogenesis. If the matter-antimatter asymmetry is not determined by a unique dynamical mechanism, if, in different bubbles of the multiverse, it takes different values, then asking, why is the asymmetry exactly 1 in a billion in our universe, might be the wrong question. The right question might be, what range of asymmetry values allows observers to exist? And the answer might simply be, values not too far from 1 in a billion. Too small, and there's not enough matter to form stars and galaxies. Too large, and, well, it's not obvious there's a too large problem, but the point is that we, as observers, can only find ourselves in universes where the asymmetry is at least sufficient for structure to exist. This is the anthropic principle. The observation that the constants of nature we measure are constrained by the requirement that we exist to measure them. Not because the universe was designed for us, but because the universes where the constants were very different don't contain anyone to notice. Steven Weinberg famously used this logic in 1987 to predict the cosmological constant, dark energy, before it was observed. He argued that the cosmological constant couldn't be too large, or galaxies would never form. And the observed value, discovered in 1998, was roughly the largest value consistent with galaxy formation. Anthropic reasoning, applied before the measurement, made a successful prediction. Could the same logic apply to baryogenesis? Could the matter-antimatter asymmetry be anthropically selected, not generated by a specific mechanism, but simply taking the value it takes because smaller values don't produce enough structure for observers? Let's be honest about how most physicists feel about anthropic reasoning. They hate it. Not because it's obviously wrong. It might not be wrong. The multiverse might be real. Anthropic selection might genuinely explain some of the apparently fine-tuned features of our universe. The discomfort isn't about logical validity. It's about what accepting this answer would mean for science. Science progresses by making specific, falsifiable predictions and testing them. A theory that predicts a value because observers must be present to measure it, a theory that says, of course the constants are what they are, because if they weren't, we wouldn't be here to notice, is a theory that resists falsification. You can't disprove it by finding a universe with different constants, because you can only ever observe the universe you're in. You can't confirm it by counting other universes, because they are, essentially by construction, unobservable. Anthropic reasoning can feel like the end of inquiry. Like saying, the universe is the way it is because it had to be, for us. Which is, in a sense, undeniable. And also, in a sense, says nothing at all. There's a sharpness to this critique. If the matter-antimatter asymmetry is anthropically determined, if there's no specific mechanism, no equation that uniquely predicts 1 in a billion, then we are not going to find the answer in any laboratory. Not in Dune. Not in the NEDM experiments. Not in the FCC. We can search forever and find only upper limits, only absences, only the frustrating silence of a universe that isn't hiding a secret. It just has no secret to hide. And many physicists, perhaps most, are not prepared to accept that. Not because they're emotionally attached to a specific theory, but because the history of science is a history of finding mechanisms. Of discovering that things that looked arbitrary or miraculous had specific, calculable, physical explanations. The orbit of the Earth around the Sun wasn't fine-tuned by God. It was determined by initial conditions and Newtonian gravity. The charge of the electron isn't a magic number. It emerges, we hope, from some deeper structure we haven't yet found. Baryogenesis could be like those things. Could have a specific, unique, calculable explanation. A mechanism that, once we find it, will seem as natural and inevitable as gravity. The 1 in a billion number, once we understand its origin, might not seem fine-tuned at all. It might seem required. Or it might not. It might really be a lottery ticket. And we might be the winning ticket, looking at the numbers on our face and mistaking luck for law. The uncomfortable truth is that we don't yet know which story is true. But here is what makes physicists keep going. Keep building. Keep measuring. Keep thinking. Even if the multiverse is real, even if anthropic selection plays some role in determining the constants of our universe, there must still be a mechanism. The anthropic principle selects among possible universes. It doesn't generate them. Something still has to produce the bubble. Something still has to break the symmetry, in each individual universe, to determine how much matter survives. Even in a multiverse, baryogenesis has to happen. The Sakharov conditions still have to be met, in some form, in every universe that contains matter. The multiverse doesn't dissolve the baryogenesis problem. It just potentially explains why the result takes the particular value it does. The mechanism still has to exist. We still have to find it. And finding it means confronting the deepest symmetry question in physics. Not CP symmetry, the one we've already cracked. Something deeper. CPT symmetry. We mentioned this before, the theorem that says if you simultaneously reverse charge, parity, and time, the laws of physics are exactly the same. This is not an experimental result. It is a mathematical theorem, derived from the foundational structure of quantum field theory. Any local, Lorentz invariant quantum field theory, any theory that respects special relativity and treats space and time the right way, must conserve CPT. It is not a symmetry you can choose to break. It comes with the mathematics, as inevitably as 2 plus 2 making 4. And yet, CPT violation would explain everything. If CPT is not exact, if there is some regime, some energy scale, some domain of physics where CPT fails, then matter and antimatter are not constrained to be mirror images of each other even at the deepest level. The universe could be fundamentally, irreducibly biased toward matter. Not because a specific process produced more matter than antimatter, but because matter and antimatter are genuinely, inherently different things, at a level so deep that even our most fundamental mathematics doesn't capture it. This would be the most radical result in the history of physics. More radical than quantum mechanics. More radical than relativity. It would require throwing out not just the standard model but the mathematical framework on which it is built. Quantum field theory itself. The language we use to describe all of particle physics. Most physicists think this is very unlikely. The evidence for CPT symmetry is extremely strong. The alpha experiment, measuring the spectrum of antihydrogen, is essentially a direct test of CPT in the lepton sector. Neutral kaon oscillations provide some of the most precise tests of CPT symmetry ever performed. Every result is consistent with exact CPT. But extremely unlikely and impossible are different things. And the history of physics is littered with symmetries that everyone thought were exact, right up until the moment they weren't. Parity symmetry was thought exact until 1956. CP symmetry was thought exact until 1964. The universe has a habit of breaking rules we thought were unbreakable. If CPT falls, even slightly, even at energies we haven't yet reached, everything changes. The matter-antimatter asymmetry isn't a mystery to be solved. It's a feature. A fundamental property of the universe, built into its deepest structure. Matter doesn't just happen to predominate. It is preferred. By the laws themselves. And if that's true, the question isn't, why is there more matter than antimatter? The question is, what are matter and antimatter, really, and why does the universe love one of them? There's one more thread we need to pull before we reach the end of this story. One more deep connection that most explanations of the matter-antimatter mystery leave out, and it's the one that, once you see it, makes the whole thing feel even more enormous. Time. The CP violation we've been discussing, the crack in the mirror that lets the universe treat matter differently from antimatter, is, by the CPT theorem, equivalent to a violation of T symmetry. Time reversal symmetry. The laws of physics, under CP violation, are not the same when you run the clock backwards. Think about what that means. The fundamental laws of physics are, at the deepest level, almost entirely time-symmetric. A movie of two billiard balls colliding looks the same whether you run it forwards or backwards, both directions obey Newton's laws. A movie of an electron and a positron annihilating into two photons looks the same forwards and backwards. At the particle level, almost every process is reversible. The laws don't have a preferred direction of time built into them. And yet, we experience time as having a direction. Profoundly. Irreversibly. Eggs break but don't unbreak. Heat flows from hot to cold, not from cold to hot. You remember the past and not the future. The universe began in a state of low entropy and is evolving toward higher entropy, the second law of thermodynamics, and that one-way evolution is what gives time its arrow. The standard explanation for the arrow of time is statistical. It's about entropy, about the overwhelming probability that complex, ordered systems evolve toward disorder. It's not a fundamental law. It's an emergent feature of how large numbers of particles behave collectively. But CP violation, T violation, is something different. It is a fundamental, particle-level asymmetry in time. A specific physical process, the decay of a kaon, the oscillation of a B meson, that runs differently forwards than backwards. Not because of statistics. Because the laws themselves are different in the two directions. And this T violation, this particle-level arrow of time, is intimately connected to the matter-antimatter asymmetry. They are, through the CPT theorem, two sides of the same coin. The universe's preference for matter over antimatter and the universe's preference for forward time over backward time are not independent facts. They are linked. Deeply, mathematically linked. Which means that when we finally understand why the universe contains more matter than antimatter, when we find the missing CP violation, the mechanism of baryogenesis, the physics beyond the standard model that tilted the balance, we will simultaneously understand something profound about the nature of time itself. Why time runs forward. Why the past is fixed and the future is open. Why the universe is an arrow pointing in one direction, from the Big Bang toward whatever comes last. The matter-antimatter mystery is not just a question about particles. It is a question about time. About why the universe has a story at all, a beginning and a middle and an end, rather than a timeless, symmetric, directionless equilibrium of nothing. Let's come back down. All the way down. From CPT theorems and multiverse landscapes and the arrow of time. From leptogenesis and sphalerons and the electroweak phase transition. From all the machinery and mathematics that we've been building, layer by layer, for the past hour. Let's come back to something small and immediate and human. Your hand. Look at it. Or just be aware of it, the weight of it, the warmth, the astonishing complexity hiding inside something so familiar you've stopped noticing it. Roughly 30 trillion cells, each one a universe of molecular machinery running 1,000 simultaneous chemical reactions. Inside each cell, a nucleus. Inside each nucleus, chromosomes. Inside each chromosome, DNA, a molecule built from carbon and hydrogen and nitrogen and oxygen and phosphorus, atoms arranged in a sequence so specific that its information content would fill several thousand books. Those atoms. Follow them back. The carbon in your DNA was forged inside a star. A star that formed from a collapsing cloud of hydrogen and helium, billions of years ago, in a galaxy that was already ancient. That star lived and burned and eventually exploded in a supernova, a catastrophe of such violence that, for a few weeks, it outshone the entire galaxy. In that explosion, heavy elements were forged, carbon, nitrogen, oxygen, iron, and scattered across space. That scattered material drifted for millions of years, cooled, clumped under gravity, and eventually became part of the molecular cloud from which our solar system condensed. 4.5 billion years ago, the sun ignited. The Earth formed. Oceans appeared. Chemistry happened, the right molecules in the right environment, with the right energy sources, and at some point, in some warm shallow pool or deep-sea vent or ice grain in orbit, the first self-replicating molecule emerged. Life. And from that first molecule, an unbroken chain of reproduction stretching 4 billion years, through every mass extinction and ice age and continental rearrangement, produced you. That is the story of your hand. 13.8 billion years of cosmic history, written in flesh and bone. But that entire story, every single step of it, from the first star to the first cell to you, was only possible because of 1 in a billion. Because of a single extra particle for every billion annihilated pairs in the first microsecond after the Big Bang. Without that surplus, there are no atoms to fuse in stars. No stars to explode. No heavy elements to scatter. No planets to form. No oceans. No chemistry. No life. No hands. The entire story, all 13.8 billion years of it, balanced on a number so small it's almost not a number at all. And we don't know why that number isn't 0. Here is something worth noticing about the matter-antimatter mystery. It is, at its core, a story about 0. 0 is the most natural number in physics. When a system is in perfect equilibrium, when it's symmetric, balanced, undisturbed, the answer is always 0. 0 net charge. 0 net spin. 0 net baryon number. 0 is what you get when you don't interfere. 0 is the default. The universe, by default, should have produced 0 matter. 0 structures. 0 complexity. The absence of 0, the 1 in a billion remainder, is the anomaly. The thing that requires explanation. And this puts the matter-antimatter mystery in a strange philosophical position. We are trying to explain not why something exists, exactly. We are trying to explain why the universe failed to erase itself. Why the cancellation was imperfect. Why the subtraction left a remainder. The something we're trying to explain is, in a very real sense, a mistake. A rounding error. An imperfection in an otherwise pristine calculation. And from that imperfection, from that tiny, unexplained deviation from 0, everything was built. This is, if you sit with it long enough, one of the most disorienting ideas in all of science. Not because it's disturbing in an emotional sense, but because it inverts what we usually think of as remarkable. We tend to think of existence as the natural state, the baseline, and nothingness as the strange thing that would require explanation. Why is there something instead of nothing? We ask it as if existence is the surprise. But the physics says the opposite. Nothing is easy. Nothing is what you get by default. 0 is the answer when the universe does exactly what its symmetries demand. Existence, this particular kind of existence, matter-dominated, structure-filled, life-permitting, is the surprise. The deviation from the obvious answer. The universe doing something unexpected. We are not the rule. We are the exception. And the exception, it turns out, is the most interesting thing in the universe. The exception built stars. The exception built consciousness. The exception is sitting here, aware of itself, trying to understand what kind of exception it is. There is a version of this story that is humbling to the point of vertigo. You are a cosmic accounting error. An imprecision in a calculation that was supposed to come out to 0. A rounding anomaly that somehow grew, over 13 billion years, into something that can look back at the calculation and notice the discrepancy. And there is another version, not contradictory, just differently framed, that is staggering in a different direction. The universe generated its own complexity from its own imperfection. The exception to the rule became the rule itself. The anomaly became the cosmos. Whatever you want to call that, remarkable, beautiful, strange, lucky, inevitable, it is the central fact of existence. Let's imagine, for a moment, that we find it. Not soon, necessarily. Maybe not in our lifetime. Maybe in 50 years, or 100. Maybe a discovery at Dune, or a signal in the neutron EDM, or a new particle at the FCC, or something no one has predicted yet, a complete surprise from an experiment designed to look for something else entirely. Physics has a long history of finding the unexpected while looking for the expected. But imagine the moment. The paper. The seminar. The announcement. The point at which a collaboration of physicists stands up and says, here is the mechanism. Here is the particle, or the process, or the phase transition, or the symmetry breaking pattern that generated the 1 in a billion asymmetry in the first microsecond of the universe. What changes? At first, on the surface, very little. The sky looks the same. Your hand looks the same. The universe doesn't rearrange itself to celebrate its own self-understanding. Stars keep burning. Galaxies keep drifting apart. Electrons keep orbiting nuclei in their quantum mechanical hazes of probability. But something fundamental shifts. The last great open question about why we exist, not in a spiritual sense, not in a philosophical sense, but in a raw physical sense, gets answered. We will know, for the first time, the complete causal chain from the Big Bang to the matter-dominated universe. We will have closed the loop. The story of existence, from the very first instance to the present, will be told without gaps. Without that one missing page. And the implications spread outward in every direction. Understanding baryogenesis almost certainly means discovering new physics. A new particle, or a new force, or a new symmetry, or some combination of all three. That new physics won't just explain the matter-antimatter asymmetry. It will illuminate the other dark corners of the Standard Model. It will almost certainly connect to dark matter, that other enormous mystery, the invisible 5/6 of all the matter in the universe whose particle identity we still don't know. Many proposed solutions to baryogenesis also produce dark matter candidates, naturally, as a byproduct of the same extended theory. It will connect to the neutrino sector, whose mysteries run deep, whose masses are unexplained within the Standard Model, whose CP-violating properties are still being measured. Understanding baryogenesis through leptogenesis would simultaneously explain why neutrinos are so light, what the heavy neutrinos are, and how the lepton number asymmetry was generated and converted. 1 theory. 3 answers. It might connect to inflation, the epoch of exponential expansion that smoothed and flattened the early universe, setting the initial conditions for everything that followed. Some models of baryogenesis are tied to the dynamics of the inflaton field, the field that drove inflation, and understanding one might illuminate the other. It will change our understanding of what the universe was doing in its first microsecond. Not just conceptually. Quantitatively. We will be able to run the simulation forwards from the beginning and watch, in our models, the matter-antimatter asymmetry being generated in real time. We will see, in equations, in numerical simulations, in the cold language of mathematics, the moment the universe decided to keep something. And perhaps most profoundly, it will settle the deepest question the Sakharov conditions raised. Was the universe's preference for matter generated dynamically, by specific processes operating in thermodynamic non-equilibrium, or is it something deeper? Is it a fundamental feature of the laws themselves? Is it written into the CPT structure of reality, or printed on top of it by accident? That distinction matters enormously. If it's dynamic, if specific processes generated the asymmetry, then in principle a sufficiently advanced civilization could, in principle, create conditions where the opposite asymmetry was generated. Could produce antimatter in bulk. Could engineer the matter-antimatter ratio of a local region of space. The implications for energy, antimatter annihilation releases energy with perfect efficiency, 10 billion times more energy per kilogram than chemical reactions, are almost beyond calculation. If it's fundamental, if the preference for matter is built into the deepest structure of physical law, then the universe is more profoundly asymmetric than we imagined. And the question of what it means to have a law that isn't symmetric, a law that plays favorites at the most fundamental level, becomes one of the deepest questions in the philosophy of physics. Either way, finding the answer changes everything. Not immediately. Not visibly. But at the level where it matters most, the level of understanding. The level of knowing, really knowing, why we are here. Let's run it. The whole thing. Start to finish. One sweep. 13.8 billion years ago, there was nothing. Not empty space, space didn't exist yet. Not darkness, darkness is the absence of light, and light hadn't been created. Not silence, silence is the absence of sound, and sound requires a medium, and there was no medium, no space for a medium to occupy. There was nothing. And then, from nothing, or from something so alien to our categories of thought that nothing is the closest word we have, the universe began. In the first instant, temperatures were incomprehensible. All 4 forces were unified. Space itself was expanding at a rate that makes the speed of light look leisurely. And then, in the first trillionth of a second, the universe began cooling. And as it cooled, something happened. Something we can't fully describe. Something that left a fingerprint we can measure but whose mechanism we can't explain. Somewhere in the churning, unimaginable chaos of the first microsecond, the perfect symmetry between matter and antimatter cracked. 1 extra particle of matter for every billion pairs. A deviation so small it barely exists as a concept. A number that, in any other context, would be dismissed as a rounding error. That rounding error is everything. The universe spent its first second annihilating itself. Matter and antimatter colliding everywhere, simultaneously, releasing floods of gamma radiation, erasing themselves in a mutual catastrophe of almost perfect completeness. Almost. 1 in a billion survived. The antimatter was gone, transformed into light. The matter, that thin, improbable remainder, was all that was left. The universe was now 1 second old. It was a hot, dense plasma of protons, neutrons, electrons, and photons. Radiation dominated everything. Matter was there, just barely, but it was subservient, outnumbered by photons 2 billion to 1, swept along in the torrent of light. For the next 3 minutes, the universe was a nuclear reactor. Protons and neutrons fused into helium nuclei. Some deuterium formed. Traces of lithium. The proportions were set by temperature and density, by the physics of nuclear reactions in extreme heat. When the universe cooled below the fusion threshold, the nuclear reaction stopped. The composition was locked in. Roughly 3/4 hydrogen, 1/4 helium, traces of everything else. The raw material of everything to come. For the next 380,000 years, nothing much happened. The universe expanded and cooled. The plasma of charged particles and photons remained opaque, light couldn't travel freely, bouncing endlessly off charged electrons. The universe was a fog. And then, at 380,000 years, the temperature dropped below 4,000 degrees. Electrons and protons combined to form neutral hydrogen atoms for the first time. The fog cleared. Photons streamed freely through space for the first time in history, the light we now detect as the cosmic microwave background, the oldest light in the universe, the afterglow of the annihilation encoded in microwaves. The universe was dark then. Truly dark. No stars. No galaxies. No sources of light. Just hydrogen and helium gas, expanding into darkness, and the slowly dimming glow of the CMB. 100 million years of silence. And then, gravity spoke. Tiny fluctuations in the density of matter, quantum jitters from the very beginning, amplified by inflation, imprinted on the CMB, began to grow. Regions slightly denser than average pulled in more matter. The denser they got, the more they pulled. The hydrogen and helium began to collapse, slowly at first and then faster, into filaments and sheets and knots. The cosmic web began to form. Inside the densest knots, gas clouds collapsed further. Temperatures rose as gravity compressed the gas. 90 million years after the Big Bang, give or take, in the darkness before any light existed, the first stars ignited. Enormous, violent, brilliant, 100 times more massive than the Sun, burning through their fuel in a few million years and exploding in supernovae, scattering heavy elements for the first time into the universe. Carbon, oxygen, nitrogen, iron. The periodic table, being written in stellar fire. Second-generation stars formed from enriched gas. Planets condensed around them. Chemistry happened. On at least one planet, on ours, circling a middling star in the outer arm of an ordinary spiral galaxy, the chemistry crossed a threshold. Life. Single cells first. Then complexity. Then multicellular life, the Cambrian explosion, vertebrates, land animals, primates, us. 100,000 years of modern humans. 10,000 years of civilization. 500 years of science. 150 years of particle physics. 60 years of collider experiments. 30 years of neutrino oscillation measurements. And now, right now, a species made of the 1 in a billion surplus, sitting in laboratories and offices and university departments around the world, building machines and writing equations and running experiments, trying to understand the crack in the mirror that made all of this possible. That is the whole story. 13.8 billion years in 4 minutes. From nothing to everything, with one improbable, unexplained, universe-saving asymmetry at the very beginning, holding the entire narrative together. That is what the 1 in a billion produced. And we are still asking why.